This gearbox doesn't just spin, it bends. But to understand when and why that's a good thing, there's a few things you should probably know. Backlash. You'll find it everywhere, from doorknobs to clotheslines, bicycles and back gears. It's the slop in a mechanical system, lost motion caused by the space between features of interacting parts. And generally, it's pretty harmless. Then again, the goal generally isn't sub-arc minute positioning accuracy under load. Which brings us to the problem at hand. My homemade 5-axis milling machine only has 3 axes.
What?
Now, it's not the first time I've tried to tackle this issue. This was my last attempt at reaching rotary machining nirvana. And, well, let's just say it didn't quite get me over the edge. I don't think that'll do too well on a full sort of 5-axis setup. Aside from the awkwardness of its form, and completely ignoring the polarization surrounding whether these are or aren't in fact gears. This homemade example of a precision speed reducer is only about as precise as I can throw it. Which unfortunately rules out any amount of the set and forget ability that adding a 4th axis is supposed to provide. Why do I feel like it runs better now that I've thrown it? So, with that particular fever dream behind me, I started looking at some more sensible options. A list which, for the record, doesn't include any of these. Mind you, the list of rotary axis suitable speed reducers is exceptionally short, and the list of rotary axis speed reducers that I can reasonably afford is even shorter. So it didn't take long to settle on a harmonic drive, or at least one of these unbranded imitations. Otherwise known as strain wave reducers, these clever little assemblies offer unparalleled reduction ratios, imperceptible amounts of backlash, and exceptionally accurate positional repeatability. Right where I left it. All conveniently achieved with a part count slimmer than a cane toad's shadow at noon. Now, I know that sounds pretty complex, but if we ignore all the materials science, mission-critical geometry, and precision machining required to get these reducers to operate, they're actually fairly simple. I mean, there's basically only 3 parts to a strain wave reducer, with most of the magic coming from the flexible inner spline ring, and the specifically elliptical wave generator in charge of deforming it. That's where the strain wave part of the name comes from, and the reduction is produced in conjunction with a regular old internal spline ring, albeit with 2 more teeth than its flexible counterpart. And because the outer ring has 2 more teeth than the inner, each full rotation of the wave generator makes those contact points walk forward by just a couple of teeth, dragging the entire output with it. The generous contact area means minimal backlash, which should make it the ideal candidate for spinning stock on a CNC milling machine. But in order for it to be even remotely useful as a rotary axis, I'll need to knock up just a few more parts. Oh, and I should probably mention that I'm not an engineer. And despite everything I just said about these gearboxes being the perfect choice for this kind of application, I was still a little nervous about whether this particular drive unit would live up to the hype. So when designing my new and arguably improved 4th axis, I decided to hedge my bets on both repeatability and rigidity by including proper closed-loop position feedback and a pretty tricky pneumatic braking system, which actually even almost ended up working, but we should really get into it. I'd like to start by noting the ideal way to manufacture a housing for all the bits and pieces we'll need to drive this 4th axis would definitely involve cast iron. Anyway, over at the bandsaw, I trimmed some hand-me-down 25mm mild steel plate to the rough size and shape of the first piece of my compromise, before handing it over to the milling machine for a very one-sided first operation. This stock was destined to become the front plate of the 4th axis, so an 8mm rougher cleared the bulk of the material in the way of mounting our drive, and added some clearance to hopefully aid in eventually bolting the whole thing down. There's obviously a bit more going on here, but these features will make a lot more sense later when I'm struggling to put the whole thing together. For now, I've just got to flip it over and take care of the other side. Simple, right? So I definitely shot myself in the foot with this part. There's nowhere to really grab it from. I'm gonna have to mill up a bit of a fixture plate. Thankfully, I picked up some aluminium. Once I had a fixture plate, I was ready for Op 2. Wait, no, sorry. I still had to make a fixture to go on the fixture plate. You know, every time I walk up to this machine, it feels like there's not a step forward that doesn't take 2 steps back. I'm hoping the 4th axis makes things a little easier in the work holding department, but as with most of the tools, I've convinced myself that I can't possibly live without. It's probably only going to be an advantage in a very specific handful of edge case scenarios. Now that's a fixture. And until it's actually operational, that unfortunately doesn't include making parts for itself. So I was more than happy to let PCBWay take care of the slightly less exciting bits. See, aside from being a leading manufacturer of custom printed circuit boards, PCBWay offers a huge range of CNC machining services to help you bring your projects to life. So follow the link in the description to find out more. This second operation gave the backside of the front plate a whole load of features which, again, will make total sense in just a minute. Well, maybe not total sense, but it should at least become clear what I was hoping to achieve. After some abrupt defixturing, I refixtured the plate vertically and squared up its mounting face before carving out a keyway. 4 M10 bolts would handle the critical connection between this plate and the base of the whole assembly. So I bored out 4 holes, then milled the appropriate thread in each. Oh yeah. Note that the outer and inner pairs are slightly offset, lending a little extra stiffness to the whole shebang. The last step was to flip the part once more. Flatten the top face, and add a slot for a seal that was more of an afterthought than anything else. With the front panel complete, I could turn my attention to the braking system, which was made maybe a little more complicated than it needed to be by the fact that I decided to use such a compact bearing and reducer assembly. See, rigidity is the name of the game when building machine tools. And thanks to the all-powerful inverse square law, a structural member that's twice as long will be 4 times as wobbly. If you like structural members, you should like the video, and if you subscribe, I'll know you want to see more. So, in order to fit the brake in, without forcing the workpiece all the way out into the breeze, I decided to mount the actuation mechanism behind the front plate and have it act on the rotor with the help of some pins passed through the housing. But I still wanted to keep the whole assembly as compact as possible, which ruled out the easy route of installing a huge pneumatic cylinder. So this lift plate will be bolted to the back of the front plate, applying a constant braking force to the rotor with the help of some carefully selected springs. To release the brake, I plan to employ a couple of 16mm cylinders in conjunction with my friend and yours, the inclined plane. A pair of 2.86 degree wedges would be driven upwards by each cylinder, multiplying their measly 170 newtons to a number roughly 20 times as large. At least, that was the plan. Starting on the lathe this time, I took the opportunity to face both sides. Then I punched a slug from the center using an annular cutter. to aid work holding and reduce pocket clearing pucker potential. First up was carving the outer contour. Then I bored clearance for the 4 mounting bolts, before a bit of premature chamfering. I mean, it definitely would have saved a tool change or two to wait until I'd bored and reamed these brake pad pass-through pinholes. Holding on for the second run was simple. Thanks to the ledges I'd left for those wedges, so I quickly got to cleaning up the face and properly chamfering the outer edge. Then I just had to bore out some big holes, and a bigger one, and add a counter bore to the bottom of those blind reamed holes from op 1. The last step was to bore and thread the cylinder mounting holes, one on each of these ears, but something went awfully wrong in my probing cycle, and the first hole ended up completely out of position. That hole is not where it should be. I take full responsibility for this cock-up. No doubt directly caused by the thought that this was shaping up to be probably the nicest looking part I'd ever made. I feel like this could be the nicest looking part I've ever made. I mean, aside from this other little love tap. But I wasn't ready to scrap it just yet. Using the TIG torch and some filler rod, I patched the errant half of the hole as best I could, before loading it back into the mill and doing an actual proper job of probing. Despite the higher hardness of the frozen weld pool, I was able to bore out the correct hole and mill in an M10x1 thread, and the other ear got the same treatment. Beautiful. Gorgeous. 2 shallow wedges were next, and an order of magnitude simpler. The outer contour was milled from above. Then they could both be flipped, flattened and chamfered. My nice new fixture plate made the third setup a breeze, letting me carve in the needle roller ramps. And the final step was a simple threaded hole for attaching them to each cylinder. Which is great and all, but these wedges won't be much use without their slimline counterparts, made in much the same way, and then pressed into these slots in the faceplate. And with those parts in place, it was time for a test fit, and yet another encounter with my arch nemesis, pneumatic cylinder force calculations. Alright, let's see how we go. Oh, you're kidding me. Come on. But now wasn't the time to be mucking around with braking systems. I mean, this video was supposed to be about gears that bend, not springs that won't. Damn it. And if we're gonna find out if gears that bend really are better, there's a few more parts to tick off the list. When designing machines, you've obviously got to think about how the whole thing goes together. And by extension, and in consideration of entropy, how it all comes apart. And this isn't something I didn't do for this project, which is what led me to the decision to attach as much of the gubbins responsible for driving the 4th axis as possible directly to that front plate, hopefully making assembly and alignment that much simpler. Of course, there's not a whole lot of simple about it, and with everything packed in and strapped on so compactly, the bracketry required for mounting the motor, output encoder, and 5-way braking solenoid was going to need more than a little mysticism. Luckily, this video is sponsored by Onshape, which is about as close to a spellbook as it gets, at least within the realm of computer-aided design. Onshape is a full-featured CAD package, with all the good stuff you're used to. Parametric design, simulation, and rendering capabilities, just to name a few. But get this, it's built entirely in the cloud, and runs on a web browser. That means you can use it basically anywhere, on basically any device. Like a seance for scope creep. And you can finally say goodbye to the premature exportation. With Onshape's Git-style version history, every design decision is safely stored in real time, enabling effortless revision and carefree collaboration. You can roll back, branch off, or share with a click. So whether you're trying to keep track of whose final version is actually final, or just looking for true design freedom, Click the link in the description to try Onshape Professional, free for up to 6 months. With a little bit of digital wizardry, I filled the space between my floating parts with something roughly bracket-shaped, and completed the ritual with some carefully extruded glass fibre reinforced ABS. And once the servo motor, encoder and solenoid valve are installed, it's pretty obvious why solving the braking system's lack of power was never a matter of just sticking a bigger cylinder in. But there's more to this brake than the lift plate, like this dynamic pad, and of course the rotor. The rotor itself would be coupled to the output side of the strain wave reducer through a collection of arms, axially flexible but radially stiff. At least I hoped they would be. Anyway, hopefully that would allow the rotor to flex forward enough to contact the static cover plate and be clamped in place. Now, generally steel on steel isn't the best option for brakes, and not because it ain't grippy. In fact, as long as it's dry, the static coefficient of friction of steel on steel is actually higher than that of real, actual brakes. No, the problem is galling, and the dryness that gives us the grip just makes this worse. Thankfully, in this case that shouldn't really be a problem, as the brake will definitely only ever be engaged when the axis is stationary. Well, that didn't take very long. The rest of the housing was comparatively simple, consisting of 5 more keyed plates with less than a dozen noteworthy features between them, the majority of which we can find on the base plate. Firstly, 2 pockets ensured the dual cylinders and their air supply lines were properly clearanced. Next, mostly for the sake of aesthetics, a bit of action with a bullnose created a chamfer approaching celestial scale, to make its joint with the faceplate seamless. Admittedly, the noteworthiness of this feature comes down to the ineffectual nature of its implementation. I'm still scratching my head about where this ½ mm came from, but the only thing it'll hurt is my pride, so we'll move right along. The third feature of note, born of an inattentive tool change, was an extra hole with a cobalt high-speed steel plug. Small carbide end mills are indisposable for these situations, and as it turns out, quite disposable as well. The other features baked into this part will eventually become apparent, but the next thing I'd like to note is the importance of double-checking models of parts you've decided to outsource. I'm really clever. The way you know is that these holes are M5 threads, especially models which should have received a change to their threaded holes. They should have been M4. But I put M5 on the drawing, so that's what they are. And especially when the updated hole size is smaller than its precursor, because you can't undrill a hole, and you really can't get upset that a part was made to your exact specifications. There was no point dwelling on the hot dog down a hallway fit of the intended M4 fasteners in these M5 holes. But there was also no space for an off-the-shelf threademption, and I still really didn't feel like making any more rectangles. Luckily, as it turns out, there's just enough meat on the socket head of an M4 cap screw to mill an M5 by 0.8 thread, or at least 60% of one, resulting in a set of pretty strange looking studs. And I could cleverly circumvent the fact that these cutouts were too small to swing a socket, with a collection of custom barrel nuts. Having narrowly avoided the scrap bucket, the top panel was good to go. But to get power, air and control into the housing, the rear panel received another few holes for an anal mount lug and a couple of Ushin pneumatic connectors. The P's silent. Having finally laid my hands on a JST crimping kit, the internal wiring was relatively straightforward. Once I'd soldered up the 26-pin panel plug, crimped each cable and clustered them into pairs or pairs of pairs, mirrored by matching crimped cables connected to the solenoid encoder and servo, I could just plug them in. Ordinarily, this would be about the point that I complain about tuning servo motors, but thankfully the one I bought this time actually came with some software, facilitating an auto-tuning routine and a distinct lack of headaches. Those would come later, and be entirely of my own making. With all the parts laid out in front of me, and a huge chunk of the software configuration squared away, I'd love to say it was time for the final assembly. But really, it was just the first of the final assemblies. You know, the one where you discover the faceplate has a mile of runout. I'll save you the dread of my entire investigation, but after ensuring clearance on the rotor's mounting tabs, and the faceplate itself weren't to blame, I discovered the drive unit was the cause of my troubles. No doubt this was something to do with my sense of curiosity, in that the first thing I did with the drives after taking delivery was to fully disassemble them and investigate the devilry within. A little more inspection revealed that there was obviously a correct orientation for the components to mount in. So by reclocking them correctly this time, along with a little selective torquing of the faceplate mounting hardware, I was able to get it pretty close to perfect. Don't worry, I'm as physically repulsed by that as you are. I've actually already come to terms with the fact that this won't be my last attempt at a precision rotary fourth axis. I'm just waiting for my wallet to get on the same page. I started the second final assembly with a little more confidence, not to mention cinematographical intention. So let's take this opportunity to see how the whole thing goes together. Like I mentioned earlier, I went to great lengths to have everything build off the front plate, so that's where we'll begin. By attaching the reducer with 9 M3 cap head machine screws, remembering to add a dab of Loctite to each. The 3 holes left unfastened will be handy for mounting the motor, but first I'll turn my attention to the brake lift plate. After applying some more Loctite to the threaded ends of the cylinder shafts, I screwed them into their respective wedges, making sure the 2 sides had equal strokes before tightening the lock nut. Then I could thread the cylinder bodies into the plate and nip up a grub screw to keep them there. Some little needle roller bearings, complete with cages, and a little grease would help keep friction to a minimum once slipped between wedge and plate. And you might be wondering why I chose to use just 3 rollers for the opposite side of those wedges. The honest answer is, with the lift plate in position, I added the 4 spring stacks and mounting hardware before plumbing up the cylinders and making sure it still did what it was supposed to. Some tweaking of the preload made it so. Then I could flip things over to fit the dynamic brake pad, the rotor, and the cover plate. When torquing down the faceplate, I'll need to keep an eye on that runout. So for now, I'll get the motor, belt, and pulleys mounted. I know using 3D printed pulleys here isn't the best option, but I promise I'll intend to machine one later. I'll add the 5-way solenoid valve in charge of controlling the brake, and the 20,000 line hollow shaft optical rotary encoder. Then I can mount the faceplate to the base plate, sandwiching a key for alignment and some thread sealant I was sure wouldn't do, well, nothing to prevent coolant ingress, and reefing down on those 4 M10 fasteners to hold it all together. With one of the side panels keyed in place, I installed the front cover plate seals, printed in TPU, and followed up with the faceplate, just loosely attached for now. Then I could insert the shaft responsible for transmitting rotation to the encoder and temporarily connect the air, signals, and power required to spin the faceplate. And after that, it was just a matter of turning, tightening, turning, loosening, turning, and tightening again, until I felt like I could sleep at night. The rest of the panels went on next, and with a little cable management, they fell into place without a hitch. And with just a couple more bits and pieces, I had myself a fully functioning, servo-driven strain wave reducer, rotary 4th axis, with closed-loop position feedback and a brake. Well, presumably. Frankly, while writing this script, I wasn't quite ready to completely relive the agony I faced in the first few days of trying to operate this thing, so I'll have to keep it quick. 3 top tips for troubleshooting your high-torque, zero backlash, 100-to-1 gear-reduced servo-driven 4th axis, featuring dual-opposed pneumatic wedge floating disc clamp brake assembly, including but not limited to its motor, strain wave reducer, rotary encoder, clamping assembly, and all other unforeseen and miscellaneous means of self-destruction built directly in. Seeking the source of intermittently inconsistent encoder counts, it could be anything. As a first step, always ensure the integrity of all electrical connections. Made the assumption that your encoder and its alignment are accurate throughout a full rotation? Think again. Repeatable error in commanded versus actual angular position can easily be addressed in Linux CNC.
Why is that not 90 degrees?
Assuming you can measure the error and you get the formatting right.
Well, that didn't take very long.
Experiencing a sudden refusal to rotate? Don't worry, you've probably just forgotten to release the brake. Simply remove the faceplate, rotor cover, and the rotor itself. You're likely to discover severe galling has occurred between the rotor and dynamic pad. Remain calm and reinstall the rotor cover and faceplate. Dispose of the rotor responsibly and hope to whichever god it is you worship that the brake wasn't even necessary in the first place. You'll get around to making one from a more suitable material one day, I'm sure. Congratulations. You're now ready to find out if any of this was worth it.
It's time to solve this thing. Maybe.
My dearest Rowan, enclosed you will find a gift you will either love or loathe. A puzzle. Ah, sick. I'm gonna love it, obviously.
Nothing is certain when you can't see the maze.
No tools are permitted.
Does a torch count as a tool?
No excess force is required. With love, Brandon. I don't know if I'll be able to solve it right now.
I'm supposed to be editing the video.
I'm pretty sure
that there's a hole on this brass bit that I need to line up with this hole so that I can poke it with this stick. Where is that hole? Maybe I hallucinated it. That's a red herring.
How far out does the maze go? Is that the most?
Well, I think I've had it one step further. The hole that I thought I saw was around here somewhere. Because the other idea was that this needs to push back in at some point to allow it to come out all the way. Yeah, look, see. Aha. See, there's a hole in that.
Oh yeah.
So that I need to align with that. So it's just a matter of getting it to that point. I'll just show you later once it's... But then the tricky part is the fact that the hole is like directly opposite this. So like I can't get it lined up with this hole.
Okay.
Because as far as we know, the maze hasn't actually ever gone. Do you know what I mean? I'm wondering if I had it at that point where I was like poking it, is what I want to know. Is that a hole? That is a hole. What's that hole? Why is there a hole there? Wait a minute. That hole is the size of this. I think this pin pushes into the cylinder and then the whole thing
lifts out.
comes out. That's cool. Okay.
You just gotta get it around the other side.
Just gotta get it around the other side. What the heck? Have I gone past it again? Wait. That's it.
Oh, that is so satisfying. Imagine if it does nothing.
That would be hilarious. Did I push it in far
You
enough?
did. Yeah, I had a click, but maybe good measure.
If that's a red herring, I'm gonna be pissed.
Is there a fucking maze on the inside of the... Oh, hang on. There's a fucking... Because right now that pin is sticking out of the inside of this.
Yeah.
So, and it's captured in a slot inside this.
Okay.
Oh my god. That's crazy. You're madman, Brandon.
The most exciting part for me is when we finally solve this, we can watch his video.
Yeah. Where is it? Should I try putting this back in?
Oh.
Thought we had it. There's a part that's catching there. I need to like...
No excess force.
Oh, hang on. Wait. Feel that. There's a point in its rotation that it gets sort of stuck. Let's go back. Feel that?
It's like a little,
There's like a nubbin.
yeah.
Alright, that's enough. There's nothing to poke there. Maybe there's another thing to poke in there? Is there? No. Because also it's stuck now, like there's no way to go backwards.
If there's a nubbin side to side, maybe you have to press down.
No excess force, Holly. There's more movement in that
Oh.
than there was before, I feel. Wait, no. I can see that there's a pin here.
Oh, yeah.
See that?
Yeah.
But I can't push it any further.
That detent has to be something.
I didn't do that before, did I?
Yeah. Oh.
Use the tools provided. Okay. Magnets. What did I do? Oh, right. Okay, cool. Yes! We solved it.
Is that it? There's something in there.
There's something inside. Am I allowed to use external tools to get the thing out? Do you think?
Well,
Or
maybe
is
you have
that
to
part
go
of the
through the
puzzle?
whole maze again. It's the tiniest, weediest little...
Tradie shorts in the world. Alright, now you put it back together, Holly.
I mean, there's basically only 3 parts to a strain wave reducer, with most of the magic coming from the flexible inner spline ring. And the specific... Don't look at me like that. Do you like that?
Very good.
Cinematographical. I had to look up the pronunciation. Did you want another one of that? Was that weird? You had a smile on your face.
I was thinking of whoa.
No, it's fine.